Are we ready to go?
Test one.
Okay. Good afternoon. I'm calling the meeting to order, the Jefferson County Water Advisory Committee, July 15th, 2026 meeting. I'm calling the meeting to order, and first order is to determine our members present and existence of a quorum. We have 5 members present, and we have 2 members on the Zoom, Elizabeth Reardon and Will Smith. Appreciate they were not able to attend in person, but appreciate them being present and listening in. I want to start the session with a public comment period. If there's any public comment, there's a microphone right here. Calling. Yeah, I don't have the sign-in sheet. Do you want to make a comment? You just give us your name and your address. Thank you.
I'm Mark Kozar.
Oh, Mark, I'm sorry. We're going to have a public comment first. I'm sorry, Mark.
Okay.
Go ahead, Dr. Weimer.
No? Yes.
Yeah.
Okay. Sorry. My name is Christine Weimer and I represent Jefferson County Foundation. The foundation was reviewing the packet for the county commission meeting tomorrow. And we were frustrated by the beginning of the submission to the county commission that reads, the Jefferson County Commission is considering requiring hydrogeological studies in limited context in accordance with state law and without duplicating the work of state agencies. The commission is most interested in studies regarding proposed uses that could draw large enough quantities of water to affect water use by neighbors. We were frustrated with this because the county commission's current zoning ordinance does not allow for groundwater extraction. So why are we looking into studies that the county can require that would only be associated with land development that would allow groundwater extraction or look at groundwater extraction? Certainly, you're not going to require farmers to do studies. No one would support that. Groundwater is for farming and rural residential uses. I think we can all agree to that. But why then would we need studies for large quantity users? No one in the county is interested in changing the zoning ordinance to allow groundwater extraction. So we therefore do not need to look into these studies. It does not seem as though this statement came from the county commission. Seems like it came from the water commission. We could be wrong on that. It's not been a transparent process. And so if this did come from the commission, we urge you to go back to your mission of protecting groundwater, not supporting development that would extract groundwater. Thank you.
Thank you. Is there any other public comment? Okay. Mark is okay. We all set?
Yes.
All right. Let me start the evening off by thanking Mark Kozar for his long tenure with the United States Geological Service and his service with that organization and service to the residents and communities with his scientific knowledge. Our notes Mark's list of a number of studies he has worked on since 1991, if I'm correct, in this county alone and other counties. Mark has been a great resource for us and for studies and for the USGS, and we are grateful for him for traveling from Charleston today to do this presentation about what what he's seeing on potential water studies, past water studies, modeling, what other counties are doing. So we have 110 slides, and Mark is going to go through them. We'll pause, we will pause intermittently, but please, and for questions as we go along from the committee. And with
Before
that,
we
I'll
get
turn
started,
over.
We have one more person online calling from a 908 number.
Oh, that is Will Smith?
That is not Will Smith.
Could it be Pasha? No, he's 202.
You'll probably want to have them identify themselves before
Okay.
continuing.
May I ask the person who is calling from the 908 number to identify themselves? I'm sorry, President Maggi. No, that's not President Maggi's number. I'm sorry, Elizabeth Reardon is the 908 number. I apologize. Okay, so she's, Elizabeth Reardon and Will Smith are on the phone, and President Maggi's going to dial in as well, so.
Okay. And so for the secretary, you can note that both Will and the 908 number are here.
Yep. Thank you for flagging that. With that, Mark, can I turn it over to you, and you have the floor?
Sure. Well, first of all, my name is Mark Kozar. I'm a hydrogeologist. Actually, my title is hydrologist with the U.S. Geological Survey. And August 4th will be 41 years of service with the USGS for me. I started my groundwater career pretty much here in Jefferson County. And basically, what I'm going to do today is talk about some of the results from the past studies that were conducted by the USGS here in Jefferson and in neighboring Berkeley County. So the first pertinent study in Jefferson County outside of the geological reports that were done at the turn of the century was a report done by Paul Biber. And the title of that report is Groundwater Features of Berkeley and Jefferson Counties, West Virginia. And that report had some water quality data that was collected as part of that study. It was the first time that nitrate issues were documented in the county with relatively high concentrations of nitrate in the groundwater. Then in 1988, I moved to Morgantown and we initiated a restudy. So basically we went, I'm sorry, let me skip too far ahead. In 1974, 77, and 78, Bill Haba did a study. It was published by the West Virginia Geological and Economic Survey. And it did a pretty decent job of looking at nitrate and bacteria contamination within the county. So I will leave these copies for the commission or for the Water Advisory Committee. Most of these are out of print. They are available digitally, at least some of these reports are. We had a companion study that was done for Berkeley County a few years later. Then in 1988, I moved from Harrisburg, Pennsylvania down to Charleston, to Morgantown, West Virginia. And I started working on a restudy of Bill Haba's earlier work. So we went and resampled about 90 wells that Bill Haba had previously sampled. And I'll talk about some of the results of that study as well. And then a few years after that, we did a companion study for Berkeley County. So there's a lot of work that's been typically Jefferson County comes first and then Berkeley County comes afterward. The last major water quality study, the comprehensive water quality study that was done was this one in Jefferson County, and that's 1991. So we're looking at what, 35 years ago?
Can you name that study?
This
Please.
one was titled Geohydrology, Water Availability and Water Quality of Jefferson County, West Virginia, with emphasis on the carbonate area. And when I came out to Jefferson County to collect data for that study, it was a very rural county. The population has increased significantly since then. There's been a major change in land use, less farming than there was 35 years ago, more subdivisions, so what affects septic systems and other sources of nutrients they're having on the groundwater is kind of undetermined, for the current period. So let me go in and start looking at some slides that show some of the results of these past studies. Let's see. Well, my slide advancer is not working. Should be. Eddie, can you take the fob out and stick it back into the
I think
computer?
It just moved.
Oh, did it? Okay, all right.
Mark, can I ask you to get a little closer to the microphone, I
All
think?
right,
Or
let me
move the
move the
microphone
mic
closer
up a
to you.
little
There you
bit.
go.
There we
Thank
go. Okay, so I'd already talked about this slide, so I'm going to skip a bunch of these. This is just looking at some of the reports that I had briefly mentioned. We have the Geological Survey Bulletin 21. That's the one by Biber, 1961 publication. Then we have the bulletins by Bill Haba. That's going to be the 1970s publications, came out in 1981. Then we've got the report that I authored in 1991. Brad Ziwa in West Virginia University did a thesis in 1991 looking at lineaments and hydrogeologic setting on well yields in Berkeley County and Jefferson counties. And the USGS did a follow-up companion study for both Berkeley and Jefferson counties looking at fracture trace and lineament analysis a few years later. The fracture trace maps, that's going to be the one by McCoy and others. Then Carol Boughton, who was stationed at the USGS Leetown office, and Kurt McCoy did a study of groundwater and aquifer geochemistry and groundwater quality in Morgan County. Then in 2007, I did an intensive study of groundwater hydrology at the USGS Leetown Science Center out near Kearneysville. And this was with respect to water availability issues for the facility. Keep going. The next one would be a companion report that was a groundwater modeling effort for the Leetown area, the Hopewell Run watershed in particular. So that's going to be the 2007B, Kozar and others publication. A couple colleagues and I did a very quick sort of preliminary assessment of groundwater flow in the Peckin Creek watershed. That was more of a water availability type of a study, not so much looking at potential directions of flow or transit times, things like that. It was more how much water is available and where is it located within the county. Ronnie Valdi and others in 2009 did a study of base flow in Jefferson County. And we measured a number of streams throughout the county during low flow periods in October and November 2007 to get an idea of what groundwater discharge was across the county. And it's highly variable depending on where the major springs are, where they discharge. You've got a lot of interbasin transfer and karst systems from one local watershed to another. So some areas are more water rich and others are more water poor with respect to stream flow and groundwater resources. So the earlier USGS studies prior to 2007 focused primarily on assessments of groundwater quality, especially nitrate and bacterial contamination, and on dye tracer studies to assess groundwater flow rates and directions. USGS studies after 2007 are focusing more on collecting data necessary for developing quantitative numerical groundwater flow models to assess water quantity and availability in a region and on-site specific groundwater studies at the USGS facility in Leetown. So we used the work that we did at Leetown, which was federally funded, as kind of like a laboratory, so to speak, where we did a lot of site-specific on-site research looking at a broad range of different types of scientific methods to better understand how groundwater flows in complex, overturned, steeply dipping karst geology. So we'll just go through a real quick synopsis of some of these previous studies. The Barber Report in 1961 was preliminary water quality data for a limited number of sites. It had a preliminary discussion of the hydrogeology of the karst and non-karst aquifers in the region. It was preliminary a discussion of typical well yields from differing types of rock. It also did some nitrate sampling for 41 samples. And it found that nitrate at that time in 1961 could be elevated. We had concentrations as high as the 45 milligram per liter EPA MCL drinking water standard at that time. The current standard is 10 and is reported as nitrogen. Back in 1960s, the MCL was based on nitrate reported as nitrate, so it has a higher standard. The results from that, we had concentrations ranging from less than 0.1 to 45 milligrams per liter with a median of 3.9. So not a lot of extremely high concentrations of nitrate in that study. Only one site exceeded the 45 milligram per liter EPA MCL drinking water standard. So then in 1981, Bill Haba went back and did a more comprehensive study in this publication. And results of that were basically nitrate data from 190 groundwater samples collected in 1974, ranged from 0.05 to 182 milligrams per liter, with a median of 17.1. 27 of the 190 sites, or 14%, had nitrate concentrations in excess of the 45 milligram per liter EPA drinking water standard. Bill Haba also sampled for indicator bacteria, and samples were collected at, I think it was 30 sites. Fecal coliform concentrations range from not detectable to a maximum of 2,745 colonies per 100 milliliters of sample, with a median of 6 colonies per 100 milliliters. So there is some bacteria in the groundwater back at that time in 1981. 63% of the sites sampled tested positive for fecal coliform bacteria. So fecal coliform bacteria comes from the guts of mammals, humans, or any type of animal, mammals primarily. So their presence in groundwater indicates fecal contamination. We also sampled for fecal streptococcus bacteria. Concentrations range from not detectable to 4,900 colonies per 100 milliliters of sample. The median concentration was 58, and 79% of the site sample tested positive for fecal streptococcus bacteria. Now, fecal streptococcus bacteria is more animal related. So, if you've got a lot of cows on a landscape, you're going to see fecal streptococcus bacteria in the groundwater. Report included a countywide potentiometric surface map, or water table map. That's the only water table map that exists for Jefferson County. It has not been done since then. Report provided a preliminary assessment of gaining and losing stream reaches within the county. So then in 1991, I went back and did a restudy of Bill Haba's previous Jefferson County work. And the report, in addition to providing more detailed assessment of bacterial contamination, we sampled every site for bacteria, whereas the previous study only sampled a subset. So that was the primary difference. We also did a number of dye tracer tests for that particular study to document directions and rates of groundwater flow. So a lot of what we know about how groundwater flows and the rate of flow is based on these prior dye tracer tests. We looked at some information on spring discharge rates. I'm not going to go into a lot of detail on that. We looked at transmissivity estimates, which is basically a measure of the permeability of the rock. So that's additional data that was collected. Results from the 3 dye tracer tests that were conducted indicated that groundwater flow rates in the karst aquifer ranged from 70 to 840 feet per day, parallel to bedrock strike, and 30 to 230 feet per day perpendicular to bedrock strike. So when I talk about bedrock strike, if you look at the Blue Ridge and it runs kind of northeast, southwest, that's the strike of the rock. So when I say groundwater flowing parallel to that, it would be flowing in that northeast to southwest direction. Perpendicular to that would be cross strike. Okay, very important concept. The bedding in Jefferson County is very steeply dipping, and in times it's over and turned. So instead of being flat lying, it's heavily folded and faulted, and in many cases it's sitting straight up and down, or it's even overturned. So groundwater tries to flow through this impermeable bedrock and it can't, so it goes along strike of bedrock, especially where there is a permeability feature between, say, like a very high calcium carbonate limestone unit and a lower, maybe a shell unit underneath. The limestone will dissolve along that bedding plane, and it'll cause a solution conduit. And so you can get very, very rapid flow rates in those solution conduits. That's where the 840 foot per day value came from, along one of these solution conduits. So in that study that I did in 91, nitrate concentrations for 70 sites ranged from 0.1 to 63 milligrams per liter with a median of 5.8. This is the 10 milligram per liter standard. It changed between the 70s and the 1990s. It went from the 45 milligrams per liter as nitrate standard to 10 milligrams per liter as nitrogen. That can be confusing. So if you read some of these old reports, and I've actually got a cheat sheet in the back of this report that explains all that, it will be useful to read that. 18 of the 62 sites that we sampled for nitrate exceeded the US EPA maximum contaminant level drinking water standard. I think in the previous study it was 14% or so. So it had gone up, a little bit. Springs, on the other hand, what I had just talked about was wells, but for the springs that were sampled, 53% contained fecal coliform and 70% contained fecal streptococcus bacteria. This is not uncommon. We've known for a long, long time that springs are highly susceptible to contamination, but the entire aquifer in karst areas, such as here in Jefferson and neighboring Berkeley County and up and down the Shenandoah Valley, are highly susceptible to any contamination at the surface. So, I'll talk about some results from some statewide PFAS sampling here later on, and a report that the Department of Health and Human Resources contracted me to do to look at groundwater susceptibility in West Virginia. We looked at some pesticides at 9 different sites, and we found, pesticides like DDT, DDE, endrodildin, and heptachlor, and some of the others were showing up in the samples. A lot of these organophosphate and organoclast pesticides were banned and were no longer being used, but they were still showing up in the groundwater. Triazine class of herbicides are fairly common, but we didn't analyze for those in samples collected as part of that study. So there's not that much information on pesticides in groundwater in Jefferson County, although the U.S. Department of Agriculture apparently did some sampling about 20, 25 years ago, and I don't know what happened to that data. I've called them to try to find it, and we cannot track it down, so it's just been lost to posterity's sake, I guess. Go to the next study. So Kurt McCoy was a colleague of mine, and I had him do 365 single well tests across Jefferson and Berkeley counties. And the primary purpose of that was to conduct a fracture trace and lineament analysis study for those 2 counties. Fracture traces are just linear features on the surface of the earth. So you'll typically see sinkholes line up along these linear features.
And Mark,
Um,
sorry to interrupt you. You have a new person online with the 304 number, 3048.
I think
If
that
they-
is President Amachi.
Okay.
Let me see, he just,
You may want to confirm who those people are for your minutes.
So some of the,
hold on just a second, Mark.
yep,
I'm confirming that the 304-820-7855 number is President Machi. Okay, thank you. Thank you. We'll record that. Thank you, Mark. Sorry for the interruption.
no problem.
Please continue.
So another reason that we did the single well aquifer test was to provide hydraulic conductivity data for predictive numerical groundwater flow models. So the two pieces of data that you need to construct a groundwater flow model are the properties of the rock or the hydraulic conductivity, and then water levels and also stream flow. So based on the potentiometric surface map and all the different water level measurements that have been made over the years, we have more than enough data to build a quantitative predictive numerical groundwater flow model for Jefferson County and neighboring Berkeley County as well. Based on McCoy's study, the Rockdale Run formation of the Beekmantown group had the highest median transmissivity of all the geologic formations or groups in the county. We also found that wells less than 300 feet deep had a higher median transmissivity than wells greater than 300 feet deep. And the reason for that is that if you're drilling a well and you hit a good flow of water at 185 feet, there's no need to go to 400, right? You've got what you need. So typically when you see really deep wells, it's because that particular well did not intersect a significant number of water-bearing fractures. So the well driller just drilled the well deeper to provide a storage pocket for that. So you'll see that shallower wells typically have higher transmissivity. This is a plot just kind of looking at the distribution of the transmissivity with respect to different features. It's hard to read the script on it, but this particular one, let me go back. The one in the lower left-hand corner is the one by geologic formation. And you can see that the Rockdale Run is going to be the one with the little black line in the middle is the median value. It had the highest median value. But look at the distribution. You can see that, you know, some formations have very, very low transmissivity and others have very, very high transmissivity. So if you're doing a groundwater flow model, you need to know what those hydraulic conductivities are. Otherwise, you're going to overrepresent some areas and underrepresent others with respect to how quickly the water flows through those geologic formations. The others are, I think the one to the right of that on the bottom right is the proximity to faults. So the closer a well is to a major thrust fault, the higher the transmissivity. And that's just the function of solution enlargement along that thrust fault or a cross strike fault. And you'll see higher well yields or transmissivity along those features.
Mark?
Yep.
I just want for a question for the audience. Can you explain quickly a definition of transmissivity?
Okay. Transmissivity is just a more technical way of expressing yield, like well yield or how much the aquifer can yield to a well. Okay. And hydraulic conductivity is the same thing. It's just multiplied by the saturated thickness of the aquifer. So hydraulic conductivity, transmissivity, and well yield are all sort of basically the same thing. Okay. So in the late 2000s, Bill Palmisano at the USGS Biologic Resource Discipline Office in Leetown had obtained some funding to look at groundwater resources for his facility there with the potential for expansion of operations. And in fact, the U.S. Department of Agriculture has a research station co-located there that was built about concurrent when I was conducting my study. It was an intensive 5-year study of the Hopewell Run watershed in Leetown and surrounding areas. We used that as a kind of like a research laboratory. We did just about every type of groundwater method and scientific test that you could think of that was available at the time, including, geochemical sampling, age dating of groundwater, Packer test, the discrete zone sampling, going down with packers and packing off fractures and looking at the water quality at depth. We did groundwater flow model for that study. We did base flow seepage surveys. We did water level measurements. We did aquifer tests. We did different types of surface geophysics, looking at the resistivity of the rock, which is a kind of like a parallel to the transmissivity. Like high resistivity rock is typically going to have low transmissivity, and then low resistivity rock is going to have high transmissivity. And then we also did borehole geophysical studies to map the fracture distribution within the bedrock across the entire facility. And this gave us a very good understanding of how groundwater flows in this complex groundwater flow system here in Jefferson County. And the same rock runs up and down the entire Shenandoah Valley. So what we learned at Leetown is applicable to the entire Shenandoah Valley. There was a water quality portion of that report. We did some additional work looking at lithology and geologic structure, and that controls groundwater flow pretty much. The low permeability units are going to have slower rates of flow than the higher permeability units. The cross-strike faults, the thrust faults are going to be major avenues of concentrated groundwater flow, usually along solution-developed conduits. So you'll see the terms diffuse flow and conduit flow bantered back and forth. The diffuse flow is basically the flow that's going through the fractures in the rock, and then the conduit flow is what's going to be concentrated in the bedrock that's developed solution enlargement along the bedding. High permeability fault and fracture zones disrupt rocks in cross-strike directions, providing avenues through which groundwater can flow across or through low permeability units. So if you're familiar with where the landfill is off of the road going out towards Leetown, it's kind of like up on the high area up on top. Well, it's kind of like near the Conococheague bedrock, which is a low permeability unit. All the flow from that landfill is heading towards a Pecking Creek, and it's trying to go down dip, and it can't get there because of the low permeability bedding. So when we have these cross-strike faults, which go perpendicular to the bedding, lots of times there's solution enlargement along those faults, and it's like a plumbing system. So, it'll go a long strike until it finds an avenue to go down dip, and then it'll go down dip along these cross-strike faults. I've got actually illustrations that show a lot of this better, so I'm gonna skip by some of this. There is an epicarstic layer within the system, which is this extremely permeable upper layer of the bedrock where the groundwater table has been going up and down for, tens of thousands of years. It's caused more solution development near the surface down to about 60 feet. But that layer drains very, very quickly. So if you were to look at, we did a lot of dye tracer tests, what happens is you put the dye in the ground in a dry period and it doesn't move very fast at all. Then you get a rainfall event, okay? Especially a major precipitation event. It'll bring the head up in the aquifer, and it'll bring that groundwater table up into this epicarstic layer, and then it'll shoot out along these different, more permeable layers and pop out at springs. So you get this kind of like episodic piston type flow that's heavily controlled by rainfall events. Groundwater velocities from the dye tracer test, 8 of them done at Leetown, which were basically a repeat of some of the earlier tests that were done for the studies that Bill Haba and I had done, ranged from 12.5 to 610 feet per day. So, you've got like slow flow, and then you've got rapid flow along the solutionally enlarged conduits. The median flow rate was about 50 feet per day, but this is primarily in the upper portion of the aquifer. As you go down deeper in the system, things get very, very tight and the fractures get tighter. And so you can end up having flow rates that are, 50 to 100 years and from across a 5-mile distance in some of the deeper portions of the aquifer. Okay, I'm going to skip through. Okay, so this is a good illustration. The red line that kind of runs through the middle of the illustration there, where you see the yellow line with the hook on it, and then you got like a red line that goes, a big long one. That's a cross strike fault. All right, and you can see all the bedding in the LiDAR image, which is a laser derived elevation map for the Leetown area. Groundwater is trying to flow basically from the bottom right corner of that illustration towards the top left corner. It's trying to go across this impermeable bedding, and it can't do it. So it flows along bedding until it hits these cross strike faults, and then it goes down dip through there. And you can see how this cross strike fault has actually breached the bedding and caused a weakness there to allow, conduit development along that reach. So the most permeable portions of that aquifer are going to be along these thrust faults and cross strike faults. All those orange lines are going to be your thrust faults. The blue line is the outline of the USGS property there at Leetown. That yellow line kind of to the top of the map, when I did the groundwater flow model for Hopewell Run, my simulated heads were too high. So I went back to the geologist who was mapping that area. His name was Dave Weary. And I said, Dave, there has to be a cross strike fault there because my heads are too high. So he went back out, and sure enough, they found that there was a cross strike fault there. So we were able to, at Leetown, very, very accurately and in great detail understand this entire flow system and how it works. And it behaves similarly in Berkeley County and up and down the Shenandoah Valley. It becomes more cavernous as you go further south down into Virginia, but here in near the Potomac River and across the river in Maryland, it's a diffuse flow karst aquifer with solution conduits in it. That's just basically looking, that big red line is going to be your cross strike fault. Again, all the red ones are going to be your thrust faults. Those thrust faults are concentrating flow. There's 3 major springs at Leetown, and it's basically conveying water down to those major springs. This is a geologic map of the Leetown area. You could see, I wish my pointer would work, but it doesn't. But the thrust faults are going to be the lines that are kind of running northeast and southwest. You've also got anticlines and synclines in there. The different types of bedding are denoted by the different colors there. So like the Conococheague is going to be your low permeability bedding that I was talking about, and that's going to form the uplands in the Leetown area. And then the more permeable units are going to be down adjacent to Pecking Creek, down near where the big springs are at the USGS facility there at Leetown. This is a surface geophysical transect that we did at Leetown. The blue areas are going to be your low resistivity areas, or the areas where you have higher solution development, conduit development, higher transmissivity, hydraulic conductivity, and typically well yields. That kind of central area with starting with the light green going down to the orange, that's kind of like your upland area. It's in the Conococheague bedrock. It's very, very low permeability, so there's not a whole lot of rapid groundwater flow or karstic development in those rocks. And then to the far left of of that cross section, you'll see another blue area with higher or lower resistivity and higher hydraulic conductivity. And those all parallel these major geologic faults and correspond to the permeability of the bedding. And this is just looking at all the geophysics in plan, in a map format. So area 3, that's where the 3 big springs are at the USGS facility. It's where all those thrust faults come together. You can see the black line is the cross strike fault coming through there. Then that area 2, that's going to be where I showed the anomaly, where I told the geologist there had to be a cross strike fault up there, and it shows up in the geophysics. This is looking at the range of transmissivity for a bunch of wells that we tested at Leetown. So basically, the bigger the blue dot, the higher the transmissivity. And you can see that a lot of the higher transmissivity wells fall on these geologic features, on the thrust faults and the cross strike faults. You get into the upland areas, kind of down in the lower right-hand portion of the map, up where you've got the Conococheque bedrock outcrops, and a lot of those well yields are not that high, and transmissivity of the rock is not that high. So I'm going to talk about a study that was funded by the health department. It was called the Surface Water Influence Groundwater Supply Assessment, or SWIGS. That was a term coined by the West Virginia legislature. They mandated that the West Virginia DEP and the West Virginia Department of Health and Human Resources assess the vulnerability and susceptibility of aquifers throughout the state of West Virginia. And the health department and the DEP contracted me to do the study for them. So I'm going to present some of the results of that study. I already went through that. Definition came from the legislature. So I want to talk about 2 concepts. One is intrinsic susceptibility, and another one is vulnerability. Intrinsic susceptibility is discussed in terms of hydrogeologic terrains. So it's basically going to be the hydrogeologic properties of the rock that make that aquifer susceptible to contamination. So in the karst aquifer, the more transmissive or permeable areas, especially where you've got solution conduits, are going to be more susceptible than the diffuse-dominated portions of the aquifer, where you basically have fracture flow in discrete fractures within the bedrock. The second term is vulnerability. Vulnerability doesn't have much to do with susceptibility. It's more, is there contaminant sources within the recharge area to a well or a spring? So you may have an aquifer that's highly susceptible to contamination, but if there's no contaminant sources in that recharge area to that well or spring, it may have a very low vulnerability to contamination. Typically, though, if it's susceptible, it's probably going to be vulnerable too. And the PFAS data kind of bears that out. So the groundwater vulnerability is the chemical and physical processes in the subsurface that affect the contaminant concentrations in an aquifer. Intrinsic susceptibility is going to be the ease with which water and contaminants can travel to and through an aquifer. So this is looking at the major aquifer types in West Virginia and all of the source water or public supply wells, and I believe also it's just going to be groundwater wells in the state of West Virginia. So the green dots are your groundwater wells, public supply wells. And what you want to pay attention to in this illustration are the yellow kind of lines on the map, especially in the western portion of the state, along the Ohio River, the Kanawha River, and the ancestral Taze Valley, and some other river basins. Those are going to be alluvial aquifers. So they're going to be sand and gravel deposits primarily on the margins of the streams. They're not used for water supply all that much in any areas except along the Ohio River. And you can see the number of groundwater public supply wells along the Ohio River is quite extensive. The kind of grayish looking rock is going to be your Mississippian and Pennsylvanian age fractured rock aquifers. The kind of the black areas are going to be areas where you have coal mines, underground coal mines. The orange is going to be your valley and ridge aquifers. And then over in the Shenandoah Valley, the green areas, the light green areas are going to be your karst aquifers within the Shenandoah Valley in Jefferson and Berkeley counties. So I looked at a bunch of different data that we had available on water chemistry, on VOC concentrations, on bacteria, nitrate, age dating samples that we had collected, and interpretive studies that were worked on in various areas of the state. And I came up with this flow chart that has on the left-hand axis, it's got aquifer vulnerability. And then across the right-hand side, you're going to look at the bottom axis is going to be your susceptibility. So increasing vulnerability as you go up the left-hand axis, and increasing susceptibility as you go across the bottom or the x-axis. The most intrinsically susceptible and vulnerable aquifers in the state of West Virginia to contamination are going to be the conduit flow karst aquifers in the Shenandoah Valley of Jefferson and Berkeley counties, and possibly some of the karst areas in the Greenbrier aquifer. Unfortunately, we didn't have much, if any, water quality data to assess the Greenbrier aquifer, and I've been pushing for a groundwater quality study for the Greenbrier aquifer for many years now, and hopefully sometime in the near future that'll get done.
Mark,
Then, yes.
can I just interrupt you? Eddie, President Maji is trying to ask a question. He might need to be unmuted or.
Okay.
It should be that way. I'm just confirming here that I can unmute.
Sorry.
Yeah.
Sorry to interrupt.
So as the joiner of this meeting, I can unmute. So.
Can he text the question to you?
I'll ask him to text it to me as well.
Okay. So then anyway, a lot of different things are going to affect the susceptibility and the vulnerability. And, you got the age of the groundwater. Young groundwater is more susceptible to contamination because it flushes through the system faster. Older groundwater takes a longer time, so it's less susceptible. Obviously, the transmissivity or the permeability of the rock is going to be a factor. And then you've got other things like, the proximity to nearby streams, is the groundwater flowing towards the stream or away from it, that sort of thing, and the proximity of contaminant sources. So all of that comes together and is summarized kind of like in this flow chart. And now I'm trying to get it's not advancing. Okay. Yeah, that's good. Now it's back. Okay. Okay. So in summary on this SWIGS report, the karst aquifers in the Shenandoah Valley and probably the Greenbrier Valley are going to be your highly susceptible aquifers to contamination, as are the alluvial aquifers along the Ohio River. So this is a very important concept because it ties into the PFAS study that I'll talk about here shortly. One factor for this area that I would like to mention is the Blue Ridge. There's only a thin outcrop of Blue Ridge rocks in the state of West Virginia, and that's basically going to be on the ridge across the Shenandoah River here, the state line. Those rocks are fairly high in radon content. So individuals that live on the Blue Ridge would be advised to test their crawl spaces in their basements for radon gas, because there's a high potential it could be present in concentrations exceeding the indoor air standard. So we did a study of basically groundwater quality within the state of West Virginia, and
Can you tell how this study was funded? I think that is of interest. How much did it cost?
which study?
The PFAS study. Are you on the?
Oh, the PFAS
Oh, I'm
study.
sorry. I thought you were on the PFAS study.
Not quite on
Okay,
PFAS
well, I'll
study
wait.
yet,
I'll hold that. I'm sorry.
but that was funded by the West Virginia legislature. 100%. And it went, it was
I'll hold that
mandated.
question till you get to that
Okay,
PFAS study.
all right.
Thank you.
So we did a statewide assessment of groundwater quality within the state of West Virginia. This is just looking at the distribution of sites that we sampled. And this is looking at, and I can't hardly read the scale right there. I'm going to have to take a peek real quick. So this particular illustration is showing total coliform concentrations in the wells that were sampled across the state. You can see that there's a higher proportion of wells in the eastern panhandle, southern portions of Jefferson and Berkeley County that had the high concentrations of total coliform bacteria. This is looking at, can you see what that says, Eddie, on the scale down there for the dots? So this illustration is showing nitrate concentrations in groundwater across the state of West Virginia. Remember how when we had talked about the SWIG study or the susceptibility study, identified the Ohio River alluvial aquifers and the karst aquifers in the Shenandoah Valley and in the Greenbrier Valley as being highly susceptible and vulnerable to contamination. Well, you can see that here with the distribution of the red and yellow dots. Okay, the majority of West Virginia doesn't have any nitrate contamination to speak of. But along the Ohio River, you can see a high concentration of sites with high nitrate values, and also in the karst aquifers here in Jefferson and Berkeley counties, you've got a high concentration of sites with nitrate contamination. Also a little bit in the Greenbrier Valley, which is going to be the kind of the blue area down there in the southern portion of the map, right there at the border between the purple and the light green.
Mark, I have President Maji's question, and it goes,
Okay.
and it addresses this. His question was, when you were contracted by the Department and Health to do a statewide study, correct? To assess susceptibility of the aquifers, what was the scope of the assessment? I think was statewide, correct? And
Yes, that's correct.
And it was the SWIG we talked about. And when was it directed?
The SWIG study would have been, oh gosh, I don't know exactly the date. It was late 2000s. You know, I could look up the date later.
Okay,
The PFAS study was also mandated by the legislature.
okay.
All right.
So the legal authority for both the DEP and health was mandated by the state legislator?
That is correct.
And
The remainder of the studies that I talked about mainly were funded, especially the county level studies. Were a lot of those, especially the earlier Jefferson County studies and Berkeley County studies, were funded primarily by the county themselves. Okay.
so the studies we're talking about, the PFAS and the SWIG, they were from the legislature or governor, or they were not, or internal direction from DEP?
They were mandated by the legislature that the DEP and the DHHR conduct those studies. And then the DHHR and the DEP contracted USGS to do the work because we have the capability to mobilize and do that type of sampling.
I think the other question we were going to say is how was it funded, but we can get to that later. So, okay, but it was mandated. Okay.
Yeah, I think that
And
that would be a question that I'm going to defer until I get a definite answer, but I'm pretty sure that the legislature either earmarked money for that or mandated that the DEP, it could have been out of their operational budget. I'm not sure how that, I
okay.
don't know the answer to that question.
All right.
so.
That was a specific question from President Maji, so we will follow up with him on
Okay,
that.
yeah. I mean, I
Okay.
could find out that answer though. you
Okay,
know,
great.
When I get back to the office.
Okay.
Okay,
Thank you.
you're welcome.
I'll
And this is looking at pesticides. So same study. Of course, most of the state, you hardly see any pesticides at all. The little colored dots, the open circles are going to be 0 pesticides were detected. Kind of like the bluish dots are going to be 1 to 2. The greens are 2 to 3, and then the orange ones are greater than 5 different pesticides were detected. So, Jefferson and Berkeley County are agricultural areas, so it stands to reason that you're going to see more detections of pesticides in the karst aquifer here than you do in other areas of the state. Okay, this is looking at gas, which is a radioactive gas that's present in groundwater. It's a decay product from uranium. It goes through a decay cycle. The highest concentrations of radon in the state of West Virginia are in the Blue Ridge rocks, right here in Jefferson County. Then the other area is going to be kind of like the Permian and Upper Pennsylvania age rocks. It's going to be in the green, light green areas of the map. So you can see there's a strong geologic control. The younger Pennsylvania and Permian rocks are more dominated by shale bedrock than are the rocks in southern West Virginia, which are more dominated by sandstone. So you're going to have a higher potential for radon in the kind of like the oil and gas areas in northwestern West Virginia and in the Blue Ridge. Okay, it's hard to see the dots on the map, but the highest concentrations by far were in the Blue Ridge. This is just looking at radon concentrations with respect to different ages of rock, and you could see that box on the far left-hand side, that's going to be your Cambrian age rocks. So these are going to be your Blue Ridge rocks. The other one that has fairly high is going to be the Permian rocks. That's going to be the second box from the right on the illustration there. The rest of them typically have fairly low radon concentrations. Some of the quaternary alluvium can have elevated radon as well. All right, so we'll talk about the statewide per and polyfluoroalkyl or PFAS study for West Virginia. So PFAS are different types of compounds, and there's literally thousands of them. The most common are going to be PFOA or Teflon and various derivatives. The other one is going to be PFOS, which is firefighting foam. And then there are a whole bunch of other different types of PFAS compounds that have been used over the years that until a few years ago, it was not known that they were potentially carcinogenic. So now there are MCL drinking water standards for PFAS, but before that, there wasn't. This particular study was mandated by the West Virginia legislature, and I commend them for conducting this study, because there are very few states in the United States that have conducted statewide analysis of every public drinking water well and surface water intake.
Mark,
So-
just quickly, the EPA has set the MCL levels, correct? This is a
Yes,
EPA
that's
from
correct.
the
Yeah,
EPA.
the EPA would set those MCLs.
Okay.
And I did not conduct any of this work. All of this work was done by a gentleman named Mitch McAdoo, who now works for the state DEP down in Charleston. So I am not a PFAS expert, but I can show you what the occurrence and distribution of the sampling was. So this is looking at just basically what are per and polyfluoroalkyl substances. I've already discussed it. It's just they're mainly fluorinated compounds with different types of molecules attached to them. And they could be short chain and long chain, and they are ubiquitous across the environment. They're used for a lot of different things. Probably the most common that you probably would have used in the past would have been, Teflon coated cookware, Tefal and stuff like that. But that slick paper that they used to package hamburgers in years ago to keep the that had like PFAS on it as well. It's water resistant applications, things like that. So there's a map showing all the community public water systems, including schools, daycares, across the state of West Virginia. This is basically showing the major geologic terrains again. You know, you're looking at the fractured rock in the Mississippi and Pennsylvania kind of in the purple. Then you got the valley and ridge rocks in the green. And then your karst areas are going to be your light blue areas on the map. And then, of course, your yellow along the streams along the Kanawha River and the Ohio River. So that's all the sites that were sampled. There was a high distribution of sites sampled in Jefferson County. If you look at the map there, you've got surface water sites are going to be your triangles, and then your groundwater sites are going to be your open circles. So a lot of groundwater sites in the Eastern Panhandle counties, Jefferson, Berkeley, and Morgan, but there are also some surface water sites that were sampled. So this is looking at the distribution of PFAS results for. And I can't read the.
And Mark, we're talking about public water supply, correct? Not wells.
Yeah, these are all going to be public water supply
Okay,
wells
thank you.
or surface water intakes.
Okay, thank you for the clarification.
So this is going to be total per and polyfluoroalkyl substances. So basically all of them added up. So basically you got the green, that's going to be below the reporting level. And then of course, the red is going to be more than 500. Units of PFAS. I think it's probably, I don't know if it's micrograms per liter or what. I can't read the scale here. But what the big takeaway is, where is the distribution of kind of like your red areas? You've got some along the Ohio River, and then you've got a bunch of sites there in Jefferson, Berkeley County that have got detections as well. A lot of the fractured rock in the interior portion of West Virginia is very low susceptibility for PFAS. There are some detects, but not nearly as susceptible as the Ohio River alluvium and the karst aquifers in the Shenandoah Valley. Of course, that was the same takeaway from the source water susceptibility study that we had done previously. We're looking again at PFOA and PFOS detects. So PFOA is going to be basically your more common Teflon type products, and PFOS is going to be your firefighting foam type products. Once again, the distribution of sites with detects is going to be highest along the Ohio River, but you also have some detects PFOA and PFOS in Jefferson and Berkeley counties. And I can get you a copy of the actual report, and it'll show up better when you look at the map up close because those dots are really, really tiny. This is looking at the total number of PFAS compounds. So the red's going to be 7 or more, yellow's 5 to 6, blue's 3 to 4, green's 1 to 2. So you can look at the distribution of dots. There's a lot of open circles in the interior portion of West Virginia, so no detections. And then here again, you've got your concentration of high concentration of PFAS detections, numbers, total number of PFAS compounds detected in the Ohio River alluvium and in the karst, Jefferson, and Berkeley counties again.
Excuse me, Mark, I have a question.
Yeah.
When was the PFAS study performed? I think you probably answered that.
It was fairly recently. As a matter of fact, it's still ongoing. Okay.
Mm-hmm.
The majority of the sampling would have been done, I believe, within the last 7 years.
Okay.
Okay. And the first study looked at raw water. Okay, so they were looking at the source water for the public water systems,
Mhm.
the groundwater wells and the surface water intakes. Then there was a follow-up sampling that was done that looked at the finished water, to see if is the filtration process taking some of these camp compounds out or not. And now they're in a more of a source identification stage. They're going back to do some targeted sampling to say, hey, okay, we've got some of these sites here in Jefferson and Berkeley County. Where's that PFAS compound? Where are those compounds coming from?
Mhm.
That work is ongoing as we speak, and I don't know when the end date on that sampling is, but it'll be a few years before we get all those samples collected.
Okay.
Is that sampling for Jefferson and Berkeley, only for Jefferson, Berkeley in the state, or is it in the Ohio Valley as well, or the?
They're going to do the source identification work wherever they had significant detections of PFAS compounds.
Thank you.
I believe that they're actually starting with the northern panhandle and some work over here in the eastern panhandle. And eventually they'll work to other areas of the state. But if you look at the maps of where the PFAS compounds are being detected, the interior portion of West Virginia, the Mississippian, Permian age, Pennsylvanian age rocks, fractured rock aquifers, and then those in the Valley and Ridge typically didn't have a lot of detections. It's going to be more in the alluvial aquifers and in the karst aquifers. Okay, so I'll just read this because I don't want to fumble this. Looking at sampling for Jefferson and Berkeley County for PFAS. 41 wells were sampled for 30 different PFAS compounds in public water supply wells ranging from large municipal wells to smaller non-community water systems such as mobile home parks within Jefferson and Berkeley counties. For the two most common PFAS compounds, PFOA and PFOS, 26 wells, or 63% of the sites sampled, had quantifiable detections of PFOA, and 15 or 37% had quantifiable detections of PFOS. The maximum PFOA and PFOS concentrations were 11 and 60 nanograms per liter, respectively. So going back to when I said in the earlier slide, I couldn't remember what the units were. It's nanograms per liter. The minimum quantifiable PFOA and PFOS concentrations were 1.3 and 0.92 nanograms per liter, respectively. So these are in extremely low concentrations, When I first started doing water quality work, we measured in milligrams per liters, and then we went to micrograms per liter, and now we're at the nanogram per liter detection limit stage for a lot of these compounds. The EPA drinking water MCLs for PFOA and PFOS are both 4 nanograms per liter. That wraps up the PFAS discussion on the Currents and Distribution Survey. And now I want to talk about some regional groundwater studies that have been accomplished here over the last 20 years or so. USGS has completed groundwater flow models for Hopewell Run and the Pecking Creek watersheds. And there was also a larger regional model developed at a core scale for the entire Shenandoah Valley. The Pecking Creek did not include all of Jefferson County, but included parts of it. The Hopewell Run, majority of it was in Jefferson County. And of course, the Shenandoah Valley model would have included all of Jefferson County.
Can you give the approximate date for these regional studies?
Yeah, the Hopewell Run would have been about 2007. And then the Pecking Creek model came shortly thereafter, a year or two later, 2008, 2009. And then Yeager did his Shenandoah Valley model about that same time frame. A lot of what precipitated this work was the last major drought that we had, which was way back in 2007 and 2008, I believe. So there was a lot of emphasis on water availability. And then, the climate patterns shifted a little bit, started raining again, and we had at one point 8 different studies going concurrently in Jefferson, Berkeley, Morgan, Clark, Frederick, and Warren counties, Virginia. So a lot of this was based on that, and it just happened to play out that way quite by accident. It wasn't intentional. That just happened to be a lot of concern about groundwater quality and water availability at that time, as there
Do you
is
consider all
today.
those counties to be part of the Shenandoah Basin, a regional
Yeah.
Shenandoah Basin that
Yeah.
Jefferson County, Berkeley are
Yes.
part of? So,
Yeah.
okay, thank you.
So all these models are available to assess groundwater recharge and weight and water availability for current conditions at different levels of complexity, obviously, to look at, future anticipated changes in climate, water demand. I will talk about another model that was recently developed for the entire upper Potomac River Basin, but I'll save that here until a little bit later. So this map is just basically showing the 3 models that were conducted. So if you look at there's a little polygon that the orange arrow for the Hopewell Run is just going to be about a 12 square mile, 15 square mile area right there around the USGS facility at Leetown. And then, of course, the Peckin Creek is going to be the other polygon that's going to be to the left of that, which is the area, it's kind of centered around the Peckin Creek, flows kind of through the center of it. It goes up to North Mountain. And then Dick Yeager's model does the entire Shenandoah Valley all the way down past Stanton, Virginia. So those 3 models are available. The only one that I consider highly detailed is the Hopewell Run model. The other 2 were more looking at overall water availability, and in the case of Dick Yeager's model, to investigate geologic structural controls on groundwater flow processes. There's 2 basic outputs from a groundwater flow model. You're going to get heads or elevation of the water table, and you're also going to get flows, simulated flows in the streams and in the springs within the model. So this is just basically showing the simulated groundwater levels for the Peckin Creek based on a groundwater flow model that I and a colleague of mine did for that basin. You can see that those lines are basically showing the general directions of flow. They're going to go towards the Peckin Creek, which is in the middle of the model, obviously. Then the ultimate discharge point is going to be the Potomac River on the north side of the model there. So what kind of data do you need for model development? Water level data, short-term and long-term. Basically, what you want is a snapshot of what the water levels look like so you can calibrate the model to that. But if you want to do a transient model and you want to show how the water table varies over time, then you need more data. And that's where continuous record groundwater level data monitoring wells is very, very helpful. Aquifer hydraulic properties, I'd mentioned the 2 countywide fracture and trace alignment analysis projects where we did almost 360 single well aquifer tests. So we've got a very good handle on the hydraulic properties for the various geologic formations within the study area here. Estimates of groundwater recharge, we have that based on base flow yields from hydrograph analysis of streams. And then, of course, the base flow studies that we conducted for both Jefferson and Berkeley County gives us calibration data that we can use in future model development. This is the base flow map that was conducted for Jefferson County by Ronnie Valdi, and I was involved with this as well. I did a lot of the data collection for it, and basically, these little different colored polygons are going to show the discharge within that stream polygon in cubic feet per square mile. So the purple areas, and then going down through the darker blues to the light blues, and then into the yellows and oranges, as you go down that scale, you're getting lower base flow discharge rates. So those areas in the purple, a lot of those end up happening to be right around Charlestown here. Those are kind of your more water I'm not going to say, I guess probably, I'll just call it water rich or high yield areas. The low yield areas are going to be the more yellows and oranges on the map. And a lot of this is based on geological structural controls on groundwater flow. So you might have a surface watershed that might be robbing groundwater from an adjacent surface water tributary and conveying it into that particular groundwater flow basin. So you'll see certain areas are prone to have higher base flow yields. This is a illustration from a report that Jeff Wiley did in for a report looking at low flow stream data for gauging stations across West Virginia from 1930 to 2002. And what's interesting about this plot is that on the left-hand side of that plot, you can see that you have a lot of these years where the stream flow was, the standardized departure was below normal, okay? And then about 1974, there was a change in climate patterns, and you had this step shift. And you see it in the stream flow data, you see it in the groundwater level data, and you see it in the precipitation data. And that continued all the way through the present time. What caused that step trend? At this point, I don't know the answer to that. I just know that it was pretty much widespread across the mid-Atlantic area. I'm not sure about other areas of the country, but you see it there. The main takeaway from this is that climate patterns shift with time. So we have been in what I consider above normal conditions since basically 1974. What would happen to long-term groundwater availability in the Shenandoah Valley if we go back to pre-1974 conditions? With the increases in population, the increases in water withdrawals, both surface water and groundwater withdrawals over time. It could happen. Or we could get wetter periods. I'm not sure. I know that if you look at some of the drought data for the last few years, we've been dry. So we're looking a little bit more like that pre-1974 period right now. Is that going to hold? Probably not. It'll probably go back more to a common, post-1974 to the present, but I don't know that for sure. It's just looking at groundwater recharge rates. I'm not going to concentrate on that too much. This particular map is showing the locations of wells where we have collected some type of data in the past. And almost all of these points have got a water level measurement associated with them. So this is going to be, I believe this is going to be both Berkeley and Jefferson County and Clark Frederick and Warren counties down in Virginia. The tremendous amount of information that you typically don't see in most counties in West Virginia and only maybe in the coastal plain areas of Virginia. So if you were to go further south into the Shenandoah Valley, like, Rockingham County or Harrisonburg, Stanton, Strasburg, Virginia, down in that area, there's very little groundwater level data that's been conducted. But all the studies that we've conducted in this, 5-6 county area have made the northern Shenandoah Valley a data-rich area for potential future groundwater model development and using the past water level data as calibration data. We've got 4 long-term groundwater monitoring wells in the area. Jefferson 526, which is at the Leetown Science Center, Jefferson 797, which is at the Freshwater Institute up near Shepherdstown. We've got 2 over in Berkeley County as well. One has data going back to 1956, daily value data going back to 1956. We've got 5 gauging stations in Jefferson County. Shenandoah River at Millville, Bullskill Run at Cabletown, Rocky Marsh Run at Scrabble, Hopewell Run at Leetown, and Potomac River at Shepherdstown. And there's additional stream gauges over in Berkeley County. that we have continuous flow data on. And these data are essential for current or future assessment of groundwater surface water availability within Jefferson, Berkeley counties and northern Shenandoah Valley. This is just basically looking at an older plot of some of the groundwater level data for Jefferson 526 and Jefferson 797. So you can see that, groundwater levels go up and down based on season. The plot on the left is showing the median value, or the 50 percentile is going to be the black triangle. So half the time groundwater levels are higher than that, half the time groundwater levels are lower than that. If I had a plot of the current data, it's been down in the lower 10th percentile for basically the last 6 to 8 months. It comes out of the orange into the green, and it goes right back down into the below normal category. I don't have a plot with that. I can get that data though. It's available on a live website, and I'll give you guys that web link, and then you can track it every day if you want. Same thing with stream flow. That's looking at the Shenandoah River at Millville. It goes through basically 2018, 2019. So it got down to a low flow period. There's a website called drought.gov, and it tracks below normal stream flow, Palmer drought indices, and things like that. You can go there and look at what the current drought conditions are for this area, and actually the entire country if you want. This is showing the distribution of our monitoring sites. You've got the USGS stream gauging stations, Rocky Marsh Run, that's at northern dot, and then you got the Potomac River at Shepherdstown, Shenandoah River at Millville, which is just to the east of us here, and Bullskin Run at Cabletown, and of course the Hopewell Run over at Leetown at the USGS facility there. So what are some of the limitations of previous study? The previous water quality studies in Jefferson County have preceded most of the modern county and state well grouting and construction regulations. So if you go back and look at a lot of that data, you'll see bacterial contamination and nitrate contamination. Don't know what the grouting requirements have done, whether it's reducing some of that contamination. Likely is, and to what degree we just do not know. For Morgan County, the only study, in that particular study, we only sample wells of newer construction meeting current groundwater grouting standards and construction standards. Largest concentration of nitrate sampled in those wells as part of that Morgan County study was only 2.6 milligrams per liter. And 69% of the sites sampled had nitrate concentrations less than the method detection limit. So, does that necessarily indicate that grouting is helping to reduce contamination? I don't know. Probably, but we don't know. We don't have similar information for Jefferson County.
Mark, just a clarification that Morgan County was done in 2023. Is that correct? So
Not quite that recent.
okay.
I could get the date for you. It's in the presentation. All the links have got the dates.
So you said that Jefferson County has more data than Morgan County? Is that?
Yes,
Okay.
but it's dated.
Okay.
Morgan County is the most recent study, and we sampled for fecal coliform and total coliform bacteria and other indicator bacteria there as well. We only had 5.5% of the well sampled in Morgan County study had tested positive for fecal coliform. If you look at some of the past Jefferson County groundwater quality studies, about a third of the wells were contaminated with fecal bacteria. I'm going to skip a lot of this. We've already talked about that. In a lot of the previous water quality studies in Jefferson County, we focused on inorganic contaminants, primarily nitrate, iron and manganese sulfate, kind of like common contaminants. But there are a broad range of trace metals, volatile organic compounds, semi-volatile organic compounds, pesticides, and now, PFAS compounds that we just really do not have a good handle on what the occurrence and distribution of those contaminants are within the aquifer. So, it would benefit both Jefferson and Berkeley County to have additional water quality studies done at some point in the future as well. Because there's also been a major change in land use. We've gone from less agriculture to more septic systems. What impact is that land use changing, having on the currents and distribution of a lot of these compounds? We just don't have the answers to those questions unless we collect the samples and analyze them. And I think I've talked about most of this, more focus on things other than the common contaminants. Any future studies would also benefit from more radon sampling, especially in the areas across the river and the Blue Ridge.
Mark, just to
Yep.
confirm, you said 1991 was the last countywide water study that was done in Jefferson County?
That's correct.
Okay.
And that was my first report.
Awesome. Thank you.
And I'm 64.
I say I'm 40
So-
years old and you've been doing this for 41 years. so
41.
That right
Yeah.
there says a lot.
Yeah. So, given the increase in population, changing in precipitation patterns and potential for drought, increased demands for water for various uses, residential, public supply, agricultural supply, industrial, and commercial supply, water bottling plants, there's a lot of talk about adjacent counties and data centers and, what are those groundwater withdrawals potentially what kind of impact are they going to have on the aquifer and nearby existing wells? It would benefit for the USGS to develop a predictive numerical groundwater flow model to help assess some of those potential effects of additional existing groundwater withdrawals on available groundwater and surface water resources.
And again, Mark, we're talking about a regional study of the Shenandoah Basin versus the water. That would be the ideal gold, the great standard that would inform all the counties who are involved in the Shenandoah Basin, this aquifer.
Ultimately, a joint unified model that covered the entire Shenandoah Valley would be the best option.
Okay.
Trying to get that funded by 2 state agencies or 3 state agencies, Virginia and West Virginia, and numerous county governments is a is a daunting task to try to secure the funding to make something like that happen. I will mention real quick, USGS, we are not 100% funded by Congress to do the work that we do. A lot of the work that we do is reimbursable funds from external agencies. So we just can't do whatever we want. We have to find cooperators at the state and local and county level to work with to make these types of studies come to fruition. So USGS has proposed numerical groundwater flow models in the past in 2007, 2021, and most recently in 2025. A lot of this is an old slide, but this is looking at the increase in population in the region between 1990 and 2000, and it's gone up even more in the last 25, 26 years. This was the proposal that I presented the last time I was here. It was looking at we were wanting to do a groundwater flow model for the northern Shenandoah Valley. And we ended up cutting that back to just looking at mainly Jefferson County and part of Berkeley County. But the study area for this particular proposed model was the northern Shenandoah Valley counties of Jefferson, Berkeley, and part of Morgan County, Clark, Frederick, Warren, and, obviously Winchester, I guess, is considered a county in Virginia, those 4 counties. What we were planning on doing was using the LiDAR imagery to help us accurately represent the surface of the model. And it can also help identify areas where you've got a lot of solution-dominated karst occurring. In that area, we had 7 active continuous record wells collecting daily data, and even 15-minute data on groundwater levels and 14 gauging stations. So there's a tremendous amount of data available for this northern Shenandoah Valley to build a predictive numerical groundwater flow model on. It's just showing the wells in those counties and the gauging stations. So this is the proposal that we presented before the Jefferson County Commission on my last visit. Doesn't go as far south down into Clark, Frederick, and Warren County, just to the next local logical groundwater divide down there, and it stops at North Mountain. There have been numerous iterations of different proposed models over the years, and I think we're getting close to maybe making something happen here in the near future after about 25 years worth of effort. What were the project objectives for that proposal? Assess current groundwater availability, assess the distribution of current groundwater withdrawals, delineate areas that have a higher capacity for high groundwater yield, assess the impacts of potential drought on current groundwater availability. And in consultation with county planners, we were planning to develop scenarios of future groundwater availability based on anticipated population growth, future development activities such as public water system expansion, new subdivisions, new commercial or industrial facilities, like water bottling plants, that sort of thing, data centers, and to assess changes in aquifer storage and impacts to existing wells and springs. We've got pretty much all the data that we need. We've got quite a few aquifer properties data from the previous fracture trace and lumen analysis maps. We've got hundreds and hundreds of water levels that can be used as calibration points for the model. We've got the precipitation and recharge estimates for the area, and we've got the previous base flow seepage surveys to use as calibration points to determine the flux of stream discharge into and out of the groundwater flow model. About 1,600 wells total in the study area that we have previous data on. Yeah, I've talked about a lot of this data that we already have. So I'll just skip forward. So this is looking at a bibliography of the previous studies that were done. I think I provided this to you, Mary, and did you post this up to a website for public access, or?
It's posted on it was posted on our public notice here.
Okay, all right. So all of the data that I talked about are presented in these publications. So you can actually go click on these links, download the data in a PDF format, and you can read it for yourself. So the main data that we would need, maybe not as much for Jefferson and Berkeley County, but for some of the other counties down further in the Shenandoah Valley, would be water levels, potentiometric surface maps, water level measurements, and synoptic seepage surveys or base flow measurements from streams flows. We have very little of that data for the areas down towards Stanton and Harrisonburg and the counties up to just south of Winchester, Clark and Frederick counties have some data, but the counties south of there have very little data. So that would be a major data limitation. Recharge is commonly estimated based on either hydrograph separation and stream flow records or you can do what they commonly refer to as a soil water balance method, which is calibrated against the base flow stream flow data, and it provides a gridded surface or recharge. That's kind of like the current state of the art for groundwater recharge distribution within a model. You know, in the aquifer properties, we've got plenty of that data for Jefferson and Berkeley County, not so much for the Virginia counties. So I'm going to give a rundown on the Hopewell Run Basin groundwater flow model. This is an example of what can be done with the numerical groundwater flow model. So this is the most detailed of all the models that we did. This is looking at the geologic map of the area. Each one of those colored areas on that map is a different geologic formation. Each one of them has a different hydraulic conductivity profile. You also see the thrust faults and the cross strike faults mapped out on the geologic map. We've got all those transmissivity estimates from the single well aquifer tests that were conducted in the Leetown area that were available as well for that to provide hydraulic conductivity data to calibrate that model. And there's looking at that data, you know, from the previous graph that we looked at before. This is basically a stratigraphic column. You've heard me refer to the Conococheague limestone. That's going to be your older limestone unit in the county. That's typically low permeability, not very karstic. The Martinsburg Formation is a shale unit. It's not limestone or dolomite. And then kind of those intermediate formations, the Rockdale Run and Chambersburg limestone and Beekmantown Group rocks or Stonehenge limestone are fairly conduit forming rocks. So they have fairly high permeability. Looking at the distribution of the resistivity, which we helped to parse out the hydraulic conductivity in the model. You've already seen these plots. You've already seen this image before. So when you take all this data from what we learned there, you put it together and you can develop a groundwater flow model from it. So the study assessed groundwater availability for facilities and found that under normal climatic conditions, current and anticipated increased groundwater withdrawals from wells at the facilities would have minimal impact on the facility springs or existing water resources. However, during drought conditions, an approximate 14% reduction in stream flow in the area was possible, and declines in water levels in the vicinity of the facility springs could range from a half a foot to greater than 1.2 feet. Now, half a foot or 1.2 foot might not sound like a big drop in water level, but it's a pretty significant drop if it occurs for a spring, because, you know, it's lowering the discharge of that spring substantially. This is the model layers. It was a 3-layer model. The upper layer is the very, very permeable epicarstic layer of the model where the rock is very, very permeable. The middle layer is going to be where the majority of wells are drilled. It's going to be moderately permeable, and then the deeper you go in the system, the tighter the rocks become and the lower the hydraulic conductivity becomes. So in this particular model, the hydraulic conductivity in the middle layer was about half of what it was in the upper layer, and then the lower layer was about half of the permeability of what the middle layer was. So the hydraulic conductivity is just decreasing as you go down within the earth, within the aquifer. This is looking at places where we had water level measurements that we used to calibrate the model to. This is the hydraulic conductivity for the upper layer of the model. If you look at it, you notice it very closely parallels the geologic map, with the exception of the cross strike faults and the thrust faults were simulated as high hydraulic conductivity layers within the model. You can see those thrust faults, the kind of like light blue areas and the cross strike faults there. they have the higher hydraulic conductivity associated with them. And if you don't simulate that higher hydraulic conductivity, you don't really simulate the aquifer properly. And any type of solute transport or flow directions that you get from it would not be as accurate as it would be if you actually simulate those high K zones. And we did that for each layer of the model, layer 1, layer 2, and layer 3. Okay. So,
Mark, I want to welcome President Pashamaji of the County Commission, and also give you, we're like 7:43, and we want to leave a few minutes for questions.
okay.
And also, I think you might want to allude to give us a
I'll-
quick briefing on Wade Sanford's
Right.
Upper Potomac.
What I
Okay.
will do is I'll
But I
finish
think you're
this up.
I think you're getting close to wrapping up.
Okay. Yeah, I'm getting
Okay.
close. So
Okay.
I'll finish up this and then we'll skip ahead to what's going on now.
Okay,
All right.
great.
So this is basically the output from the model, which is going to be the simulated heads or the water table profile, and then the black arrows are just kind of showing the direction of groundwater flow. You can see that the thrust faults and the bedding are kind of directing groundwater flow towards those major springs at Leetown. That's why those springs are there, because the geologic structure and the geology is funneling the water down towards the facility. I was able to do what they call mod path analysis and delineate the recharge areas to the 3 major springs at the facility. So there you have Blue Gray and Balk Spring. Balk Spring is going to be the one to the north, the kind of beige area. The purple is going to be Blue Spring. I think gray is going to be the green. This is just looking at very quickly simulated drawdowns due to pumping in the Leetown area. And I did that based on current pumping, based on potential additional withdrawals in the future. I did some drought predictions, looking at how much drawdown you can get in those production wells around the center springs during droughts. And then I actually did a hypothetical, what would happen if a large subdivision would go in and you'd have withdrawals there? What impact would that have on the aquifer? So I think I'm gonna skip around this. We did in the Pecking Creek model. This is basically, remember the base flow map that showed the water rich and water poor areas? We actually computed the hydrologic budget for each watershed, and that's all that data is summarized in this table right here. So recent developments, Jefferson County asked the WVDEP to fund development of groundwater flow model. The DEP is interested in funding the effort, but availability of funds is a limiting factor at the present time. The USGS does have some cooperating funding available for the effort, maybe 20%, maybe 30%, not sure. It kind of comes and goes depending on what projects have been funded and what time of year it is, that sort of thing. In the past, we've done a lot of projects in a 3-way split, usually with the USGS putting in a third and either a state agency or 2 state agencies or a state agency and a county agency, each putting in a third of the funding for the project. There's been some discussion if there's a role for the regional planning and development councils. Do they have a role in helping to look at these types of projects and the need for those types of project, and maybe herd the cattle, so to speak, to get them all together and make these types of projects come to fruition? Not sure. I don't know too much about the planning and development councils, but there are 3 of them in the Shenandoah Valley, and then here in Jefferson, Berkeley County, I think it's Region 9 Planning and Development Council, I believe. The most recent development, the USGS just last week submitted a proposal to the EPA to update an existing unpublished model for the Upper Potomac River Basin to better assess transit and residence times of groundwater with respect to nutrient management in the Chesapeake Bay watershed. Like I said, that model's unpublished and it needs to be updated with more specific hydraulic properties, which we have, and water level and stream flow calibration data. So we're very excited about this opportunity. If this model is funded by the EPA, it will provide the base model for numerous county studies or regional studies. And we could just either embed, we could like do an inset model for the Jefferson, Berkeley, Morgan, Clark, Frederick, Warren County, Northern Shenandoah Valley, or we could eventually do the entire Shenandoah Valley, or potentially we could do counties as they, as they become available, as funding becomes available, with the intent, maybe 10 years from now, the entire watershed is done, all the way from the Potomac River all the way down to, south of Stanton. That's what we're hoping for. So the first domino that needs to fall is the funding, hopefully from the EPA, which is not specifically designed to look at, water availability issues at the county level or at the regional level, but more related to Chesapeake Bay watershed issues. However, that same model can serve multiple purposes, and that's what we're planning to do.
Could you means in this context?
Okay, so residence time would just be like the age of groundwater, okay, within the aquifer. We know that based on groundwater age samples collected in the past, a lot of spring flow has a young flow component and old flow component to it. So your average age might be 2 to 4 years, but there's going to be a younger component, and then there's going to be water upwelling from deeper within the system that could be 50 or 100 years old. So you'll get an idea of groundwater ages, and then also flow velocities, or how fast it flows through the system. The deeper you go in the system, the slower the flow. We don't know what those transit rates or residence times are. And that's the major question that we wish to answer with respect to the work that we're proposing to do for the EPA for the Chesapeake Bay work, is how fast is groundwater flowing through the aquifer in the various layers within the aquifer, as you go to the shallow, more permeable parts of the aquifer, to the deeper, very tight portions where you have very, very slow flow.
Mark, I want to ask if anyone else has any questions from the Water Advisory Committee? We're got a few minutes left.
Okay. I've got a little bit more if you want me to.
Okay. We're here.
So I just talked about this. We're hoping that we'll find out whether this particular study gets funded here within the next few weeks. This is the Ward Sanford model that I said is currently unpublished. This is the model that we're hoping to take and update to create a regional model. It'll concentrate mostly on the Shenandoah Valley, but we'll also have components of it that go into the headwaters of the Potomac. So over into, Morgan, Grant, Mineral, Pendle, counties over Hardy County. But the area of emphasis that we're looking at right now is going to be within the Shenandoah Valley, basically from the Potomac River south. Ward did pretty much the same thing that I did in the Hopewell Run and the Pecking Creek models. He parsed his hydraulic conductivity out based on major rock type. But we've got better data than that. We've got data down to the formation level, like where he grouped all the carbonate rocks into maybe 2 classifications. We've actually got that hydraulic conductivity for those at the formation and group level. I think we're getting close. So, in summary, Jefferson and Berkeley counties have both been fortunate to benefit from a large number of past USGS hydrogeologic studies. There's no county in the state of West Virginia that even comes close, with the exception of Morgan County, to having the types of data available to manage water resources than what you guys here in the Eastern Panhandle have. A lot of the work that we did at Leetown has helped us to provide a better understanding of the groundwater flow system within the aquifer and how the different lithologic controls, geologic controls, structural geologic controls on how that water flows from point A to point B. And those are very important. A lot of past dye tracer test work has been done. You know, hypothetically, let's say that, you know, tomorrow there's a tanker truck accident on Interstate 81 and a slug of some type of chemical goes into the aquifer. You know, based on some of the past data that we have, we could help the state agencies get an idea of where that contaminant might go. If we had a predictive numerical model, we could even do a better job of predicting where's that contaminant going to go and how long is it going to take to get there, that sort of thing. So although much data has been collected in the past, additional assessments are needed, especially with respect to water quality and groundwater modeling. Like I said, the last quantitative water quality investigation was done when I first started my career. Back in 1988, I was collecting data, and I published this report in 1991. A lot of changes in land use here in the last 35 years. We have no idea what the quality of the groundwater is outside of the PFAS data that was collected most recently with respect to nutrient, nitrate concentrations, indicator bacteria. There are county level regulations for grouting wells now that didn't used to exist. You know, if we redid some of the bacteria sampling on the newer subset of wells that were constructed according to the grouting requirements, would we get a lower distribution of nitrate and bacteria than what we got in previous studies? Possibly. But we don't really know the answers to those questions unless we collect the data and analyze it. And I think I'm getting real close to being done. So all of the reports and data that I discussed today are all publicly available from the U.S. Geological Survey. There are links to the different reports in the presentation here and also in the list of reports that I provided to you previously that you've already posted up. So it's publicly available to anyone who wants it. Just go to the website, download the report. They're usually in PDF format, and you can look at the information for yourself. There's also a database called ScienceBase. So a lot of the PFAS data was published in the USGS ScienceBase repository. If anybody has any questions on any of these reports or any of these publications, they can feel free to call me, and I'll give you my telephone number. It's 304-542-2594. Or you could contact me at MDKOZAR, that's MD Mark David Kozar, MD Kozar at usgs.gov. Here's some web links. All these reports, the majority of them are on that pubs.er.usgs.gov website. The Water Watch website no longer exists. It was discontinued, but we have an internal replacement for it that we developed for Virginia and West Virginia. That's it. That's
When you
all I
say
have.
internal, is that available to external at all? Or
I'm sorry?
when you say it's an internal website, is that?
No, it's available to the public. It's on our internal server, but it is available to the public.
Would you be willing to make these slides available to us? We're going to post the whole video, so the slides will be available, but
Yeah, it's all published material, so
Great.
there's nothing in there that's
110
proprietary.
slides, what an opus. Do you want to make any comments?
I have a lot of thoughts on this matter that I'm going to share tomorrow during the county commission meeting. As far as questions that are technical in nature, I don't have any right now, but I really enjoyed your presentation. Thank you.
Yeah, just feel free to contact me. I prefer a telephone call as opposed to email, because that way I can ask additional questions and it ends up being less time for me to get the information that the end user needs,
Could you give me that number one more time, Mark, just in case I do want to call you and chat?
What was that, the telephone number?
Yes, sir.
304-542-2594. And I tell you what, I'll go ahead and I'll update or we can update the contact information on the slide too, with the most recent telephone number and email address.
Great, thank you.
Thank you, Mark.
Well, on behalf of the Water Advisory Committee and the residents of Jefferson County, we want to thank you for your 41 years of service. This is an opus of work, and certainly Jefferson and Berkeley County are going to really benefit now and in the past and in the future when we look at water quality, at water studies, to have this data online. And I just want to thank you. Thank you. Incredible.
And it's been a pleasure. I drove over here from Charleston and I drove along Corridor H. And I was just thinking to myself, I said, how lucky I am to be able to work in the beautiful state of West Virginia and to have spent a big proportion of my career working in the Shenandoah Valley in Jefferson and Berkeley County. And I'm not sure when I'm going to retire. I'll be around a few more years, maybe. We'll see.
Well, we're grateful for you for that. I want to thank Eddie for helping us today and thank the audience for coming, our Water Advisory Committee and those on the phone. I want to thank all the audience, and I also want to recognize Delegate Funkhauser, who has been here for the presentation. Thank you for coming. He represents us in the legislature, and I think he heard a lot about what the legislature has done to help fund studies. So I hope your ear was, I'm sure your ear was listening. So thank you very much. I'm going to adjourn the meeting. May I have a motion to adjourn?
Motion.
All those in favor?
Aye.
Aye. We are adjourned. Thank you, Mark.